Welcome to tutorial 2 and the delta Y transformation. And in this tutorial, we will use the delta Y transformation to calculate the voltage across the 35 ohms resistor. The voltage across what? The 35. So in this diagram, you realize it's not easy to do your series parallel within the network reduction when you are starting from the end. We can't do the series parallel from the end. So what we can do is, whenever you see a delta network or a Y network, you can use the transformation and change it to its equivalent. So after changing it to its equivalent, you can now apply your series parallel inside that new circuit, then get your total resistance. So we are just transforming so that we can do our network reduction. That's the business here. Just transform so that we can do the series parallel. So let's see, in this diagram we have a number of delta or pi shapes. So this 12, 10 and 20, you can see it forms what? A pi or a delta. This 35, 15 and 12 also forms another what? Pi. You can also see this 15, this 12 and this 10. It forms a Y shape or what? A T shape. So for the purpose of this tutorial, we are going to use what? The Y to delta transformation. In the next video to be uploaded, we will use the delta to Y transformation. So let's stick with the Y or T to delta. So we are going to change this T here. The T inside the circuit, the 15, the 12, and the 10. This T, which is the same as what? A Y. So we are going to change this one to what? A delta. So let's see how we can do that transformation. So let's see, I have a T. Let me draw it again. The T, which is, I'm drawing it in a Y shape. Good. So I have my 15 here, my 10 here, and what? My 12. And I'm going to change this one to a delta. So let's draw the delta around it. So as usual, I have this, a resistor will be here, delta network. Another resistor will be here. I have what? Another resistor here. So let me draw the delta. Let's say I have one value here, one value here, what? Another value here. Let's name this point. Let's say this A, B, and what? C. So A, B, C. So the delta values, I'm calling this one RAB. So RA what? B. Let's call this one RAC. AC. Let's call this one what? RBC. RBC. Now we are changing. So let's see how we can get the values. And we did that in our previous video. So if we want RAB, that's the delta value, RAB. What do? We multiply what the Y values to in pairs. So 15 will go with 10, plus 15 will go with 12, plus 10 will multiply what? The 12. Then we divide by what? We want this one, RAB. So we are going to divide by the 12. So I have 12. Let's see what we get. So we have 15 by 10 plus 15 by 12 plus 10 by 12 divided by what? 12, which gives us 37.5 ohms. That is RAB. We move on to RAC. Alright, this value. And as you already know, the numerator for this would be the same. So I'll get the numerator for the first one. The numerator gives us 450. So 450 divided by, I want RAC. So if I want RAC, I'm going to divide by what? 10. So 10, and this one gives us 45 ohms. Now it's left with RBC. RBC here. The numerator is the same. 450 divided by what? I need this one, so I'm going to divide by what? 15. And this one gives us what? Gives us 30 ohms. So these values are representing what? The delta values of this Y network. So we are now going to draw the circuit again. But where we have that Y shape, the T, we are going to replace it by the delta. So let's see how we will draw by replacing what? The Y with the delta. So let's maintain the values we didn't transform. We didn't transform 16, 35, 30, and what 20. So those values will be there. But 15, 12, and 10 will no longer come. But we will have what 37.5, 45, and 30 in that network. So let's start from the source. We have this, the source is there, the 16 is here. So let's see. Let me bring it down small. So I have my 16 here. Good. I have my 35 here. So now this point is where we have what? Our delta. So the delta is like this. It is replacing the T shape. That's the delta. So let's draw our delta inside there. So we have this. There is a value here. There is what? Another branch here for the delta. There is what? Another branch here. Let's straighten the wire. Good. So now we've replaced the T by what? The delta. I have this 30 here. This 30 is where here. Don't forget at this same point, this point, we've connected what? 20. We didn't transform. So we'll bring it. So let's bring our 20 here. So now this network is equivalent to this one. So let's write our values. I have 100 volts. I have 16. My 35 ohms is there. This is our 30. So now let's insert the values for what? The delta network. Remember this place was our RAC. We should place it at the appropriate branch. This is RAC here. So RAC gave us what? 45. So here is 45. This is what? RAB. And RAB gave us 37.5. Alright. And this branch here, that is what? The RBC. And the RBC gave us 30. And we have what? Our 20 ohms there. So now we can apply the network reduction we did in this diagram. So we can see the 30 and the 37.5 are in what? Parallel. So let's calculate its equivalent. Let's say RA, the equivalent of 30 and 37.5 in parallel. So we have 30 by 37.5 over 30 plus 37.5, and that gives us 30 by 37.5 over 30 plus 37.5, and we have 50 on 3. Let me leave it in fraction. 50 on 3 what? Ohms. So I've combined this one. I have an equivalent resistance here. But then you can also see this 30 and this 20 are connected in what? Parallel. So we can also find its equivalent. So let's get the equivalent for that one too. So let's say RB, the equivalent of these two. It gives us 30 by 20 over 30 plus 20, which is equal to 30 by 20 over 30 plus 20, and we have what? 12 ohms. 12 ohms. You can as well see this 35. When we are talking about parallel, you can use this idea when the branches are arranged like this. Okay, they are in parallel. But if you have a resistor separating them, then you can't say this and this are in parallel, but rather this and this are in series. Then its equivalent will be what? Parallel to this one. So we are just combining the portion which are in parallel so that we can reduce the circuit. So we saw this and this is parallel. This and that is also parallel because no element is here to separate them. We can also say 35 and 45 are also in parallel. They are standing like this. They are also in parallel. No element is here. But if I had a resistor here in the question, I can straightly do 35 and 45 in parallel. That one I need to reduce it from the back. Join it with this series first before they will be in parallel to 35. But since there is no element here and they are looking like this, I can just do them in what? Parallel connection. So let us calculate that one. Let's say RC. So RC is this and that in parallel. 35, 45 over 35, 45. And we have 35 by 45, 35 plus 45. We have let's use the fraction, which is 315 over 16 what? Ohms. 315 over 16 ohms. So after doing the equivalent portion, we can draw the network again and write our equivalent values there. So let us try and squeeze the circuit here. We have our source, we have the 16 ohm resistor. Now we've combined this and this in what? Parallel. So we have a single resistor value here. We have a single resistor value here. Right? We also combine this and this in what? Parallel. So that they are giving us a single resistor value here. And don't forget, we also combine this and this in what? Parallel. And they are giving us what? A single what? Value here. Very simple. So now this diagram looks very simple. So this value here is the equivalent of this and that. And we had what? 50 on 3. 50 on what? 3 ohms. 20 and 20, 30 and 20 also gave us what? 12. That's the 12 ohms here. 35 and 45 also give us the 315. The 315 over what? The 16. That's the value here. And we have what? This 16 here. And this is our source. 100 volts. So from here we can do what? Our series parallel. So our current, total current is from here. When it gets here, it splits where? This branch and that branch. And on this branch too, we have this one and this one in what? Series. So let's join them in series. Then we can do it in parallel with what? The 315 on 16. So let's say 50 on 3 in series with 12. Let's call it RD. RD is giving us 50 on 3 in series with what? 12. And we have, you can punch it together. 50 on 3 plus 12, which gives us 86 on what? 3 ohms. 86 on 3 ohms. That's the equivalent of this and that. This portion. Alright, so let's draw our circuit. So we have this our 16 here. This value is there. We have the equivalent of these two values also there. So the equivalent of those two values gave us 86 on 3. This is what? The 315 on what? The 16. And this value is what? 16. Alright, good. So let's continue. You can now say this and that. They are in what connection? Parallel. So let's find its equivalent. Let's say RE. So RE is this and that in parallel. We have 315 over 16 by 86 over 3 over 315 on 16 plus 86 on 3, which gives us 315 on 16 by 86 on 3 over 315 on 16 plus 86 on 3, which gives us 11.672 what? Let's say ohms. So RE, that's the equivalent of these two in parallel, is giving us 11.672 ohms. Now we've joined this and that, so our circuit now looks like this. Good. So this is our 16 here. This is what? Our RE, this value. That's our RE value there. So what can we do here? We have two resistors, 16 and what? RE in what connection? Series. But the question is asking us to find the voltage across this 35. Check this 35, which we didn't transform. This 35 is still the 35 here, right? But we combine this 35 with this 45 in parallel to give us what? We combine this and this in parallel to give us a 315 on what? 16. And that 315 on 16 is still the value what? Here. And now we've combined the 315 and this one in what connection? Parallel. And we got what? We got 11.672. What does it mean? It means if I get the voltage for this one, the RE is from this and this in parallel. So if I get the voltage for this one, it means that voltage will be the same as this resistor as well as what? That resistor. Because elements in parallel have the same voltage. So from here, I can get the voltage for RE, which is this. And that will help you get the voltage for what? The 315 on what? 16. So let's do that one. I think we will need to clean the main diagram so that we can do our calculation here. So from our main diagram, good. So let's calculate for what? The voltage across the RE using voltage divider. So let's call that one, let's say VRE, the voltage across RE. So VRE, if you remember voltage divider, if I want my voltage, it is my resistance. So it is RE, which is 11.672 over what? Sum of those two voltages. Sorry, sum of those two resistors sharing that voltage. So I have 16 plus 11.672. Then multiply by what? The voltage they are sharing, which is what? The 100 volts. So we are multiplying by what? 100 volts. And what do we get here? We have 11.672 on 16 plus 11.672 multiplied by what? 100 volts. And we have 42.179. So 1798 volts. So the voltage across the 11.672 is 42.1798 volts. So the idea of going back is also happening here, the same thing. So our network reduction video, I believe you guys are watching it. So the voltage here is known. Now where from this RE, as we said, it is from this and that in parallel. So it means the voltage here is the same as the voltage here. Now, where from this 315 on 16 to, let's go back. 315 on 16, what did we do? The same 315 on 16 is here, but what did we do here? We added what? We combined the 35 and the 45. In what connection? Parallel. It means still the voltage across the 315 on 16 is the same as what? 35. And that voltage is the same as the voltage across what? 45, because they were in parallel to give this one. And the question is asking us to find what? The voltage for the 35. So it means we are done with our question. The voltage across this 35 in the question, which is V, is equal to what? The voltage across what? This resistor 315 on what? 16, which is equal to what? The voltage across this same resistor RE, which is what? Resistor what? RE. And that value is what we are getting as 42.1798 volts. So we've used the Y delta transformation to get voltage across a particular what? Resistor in a given circuit. I believe after watching this video, you get time, go back, watch it till you